I'm Munsell McPhillips, and on behalf of the Amelia Tree Conservancy, welcome to The Secret Life of Trees. Today we'll explore maritime forests, what they look like, where they come from, and why they're so important to us. Now, maritime forests are a fine topic for arborists, foresters, naturalists, wildlife biologists. I am none of these. My scientific expertise is biomedical engineering, and specifically biomaterials, the study of the interaction between living tissue and man-made object, and what happens at the interface between them. From that perspective, I look at the trees and the forest and ask, how do they work? Why are they the way they are? What do they do? How is all of this connected? And outside of simple curiosity, why should we care? In many ways, science is simply the endeavor to discover what is true. What is so? And so what? Here on Amelia Island, we live on the edge, or more accurately, edges, between river and ocean, between land and sea, between forest and marsh. It's on the edges that life is most interesting. So, let's begin. Here we are, in one of the rarest and most beautiful biological communities on any coast. Maritime forests exist only in narrow bands right on the edge of the sea and are strongly influenced by it. Our forests here are not very well mapped, and as more of us move to the coast, they're disappearing, and they're disappearing quickly. As we begin our exploration, it might be helpful to remember a few rules of the road for the living world. First, there is no such thing as a blank canvas, or to use a development term, an unimproved property. Whenever we look at a piece of land, for example, if we're considering developing it, we need to remember that that land already has systems in place for managing the flow of water, the movement of soil, the patterns of the wind, and anything that we do that changes that is likely to set off a corresponding series of changes on the land and water around it. Nature doesn't like abruptness. Whenever we make a significant, sharp change in our landscape, say when we clear part of a forest, we're creating a fresh edge, an area of trees that will see winds to which they are not adapted. Unfortunately, that forest will respond in ways that we probably won't like, and that fresh edge will be blurred, probably through tree fall. The only thing constant is change. Our landscapes, our forests, are constantly in evolution. We can't really fix them in place, whether we'd like to or not. All of that change drives towards a dynamic equilibrium. The living world, our forests included, are always trending in a direction of balance. Whenever there's a disturbance in our forest or our landscapes, they respond in a way to get that balance back. The rate of change is important. Nature is wondrously adaptable, but when too much change occurs too quickly, the adaptation can't happen fast enough, and we are all left vulnerable. All of this adds up. There's really no such thing as making just a little change here or there. All of our changes are cumulative. And finally, everything is much more complicated than it appears. What do you think is special about this kind of tree? This live oak is in New Orleans, and like most of its fellows, It survived Hurricane Katrina quite well. Just take a good look at this tree for a moment and see if you can tell what makes this tree more resilient than most other species. Take your time. We'll come back to this in a few moments. Back on our own island, maritime forests start at the top of the dune line and extend in a narrow band right down the eastern edge of Barrier Islands and the mainland coast. As you can see here, we are deep in the Georgia embayment, sometimes called the Georgia Bight. While we are no strangers to hurricane winds, our position so far west of the continental shelf and the Gulf Stream usually means we're spared the worst of the hurricane damage. The past 2 storm seasons have been rough for us. Nevertheless, in most cases, we fare better than our neighbors in the Carolinas. As a consequence, our intact forest is more dense and lush than many others along the Atlantic coast. The eastern maritime forest can extend all along the Atlantic seaboard and around to the Gulf of Mexico. The essential adaptation of any maritime forest is the tolerance to salt spray. Now, we don't mean salt water, not like in our coastal marshes. What makes maritime forests special is their ability to withstand salt in aerosol form, in tiny, wind-borne saltwater droplets. This is an incredibly harsh environment in which salt directly impacts the tiny stoma, the pores on the leaf surface, through which carbon dioxide and oxygen exchange occurs. Most trees and shrubs can't survive this assault. In addition to the salt, our forests must contend with wind stress, dune migration, storm-driven erosion, and inundation. Our maritime forest plants are among the very toughest representatives of their species. As we move along the coast, the trees comprising the maritime forest varies, of course. In our region, the most important canopy species are broad-leaved evergreens, the magnolia and the mighty live oak. The loblolly pine is another important canopy tree, although it grows best closer to the center of the island and away from the worst of the salt. When we think of forests, we usually think of the big canopy trees, stars of the show. But a healthy forest requires the smaller trees and shrubs as well. The yaupon holly, American beautyberry, hornbeam, and cherry laurel all add to the stability, beauty, and balance of the forest. There are 2 other understory plants that we should know more about. The red bay is a beautiful small tree that was once widespread in the coastal southeastern forests. However, around 2002, the Asian ambrosia beetle hitchhiked to the port in Savannah in wooden packing material and brought with it the laurel wilt fungus. Many of our native laurel trees, including the red bay, have no defense against the fungus. Infected trees usually die within a few weeks, and there is no treatment or prevention. In just the last few years, the infestation has spread throughout coastal Florida and all the way west to Mississippi. The second plant we should all know a bit more about is the wax myrtle. This scrubby, unassuming little shrub is important to the health and vigor of all of the other plants. We know that nitrogen is one of the most plentiful compounds in nature. It's 78% of our atmosphere. However, most plants can't absorb nitrogen directly from the atmosphere. Wax myrtles can, or more precisely, the bacteria they harbor can. They're called nitrogen fixers because they have a symbiotic relationship with a class of bacteria that converts atmospheric nitrogen into the nitrate and ammonia compounds useful to plants. All of the other plants in the forest can take advantage of this bounty because the bacteria produce more than its myrtle host needs. Even our toughest plants are susceptible to some salt damage. We've all seen those dramatic, sculpted treescapes on the coast. They're caused by both wind and salt stress. The windward side of the tree or shrub is subjected to more direct salt aerosol, and this stunts or kills new growth to windward and results in more growth on the leeward side sheltered from the salt. Here's a nice example of a so what when it comes to salt pruning. See how the shape of the trees resembles an airfoil guiding the wind over the house? And here's just a bit down the street. Where would you rather ride out a hurricane? Houses and neighborhoods that are sheltered behind established trees at the dune line are the accidental but welcome beneficiaries of salt pruning. Now that we know a little bit about what makes up a maritime forest, we can ask how it got here. Remember at the very beginning and the rules of the road of the living world? 3 of those are especially apt here. Remember that everywhere we look in the natural world, there are systems and processes already in play, and each action is cumulative. Even tiny changes add up quickly, and finally, everything really is connected to everything else. Let's start with the maritime forest soil. When we compare it to rich, dark, fertile soil further inland, it's just pitiful. Our soils are sandy, acidic, low in nutrients and organic matter, and drain moisture so quickly that they're drought-prone. Closer to the center of the island, near Egan's Creek, the soil is a bit more peaty and has much more organic matter. But on most of our island, it's impressive that an extensive forest established at all. So how do we get from sand to soil? Let's take this step by step. Like many barrier islands, ours started as a bare sandspit over a limestone ridge. The pioneers of the plant world were the first to show up. In our case, the dune grasses are the first to settle in new sand deposits. They can survive the nutrient-poor conditions. They also host mycorrhizal fungi in their root nodules. These amazing fungi form huge networks of tiny little filaments that help plants absorb the scarce supply of nutrients, particularly phosphorus, much more efficiently. In exchange, the plants share some of their product of photosynthesis, sugars, with the fungi. Without a healthy mycorrhizal ecosystem, we wouldn't have healthy dunes or a forest at all. After the grasses are established, our friend the wax myrtle is one of the first woody species to colonize the dune ridges. As we learned earlier, wax myrtle hosts a type of bacteria in its root nodules that transforms atmospheric nitrogen to the nitrate and ammonia compounds that all plants can use. Once the grasses and myrtles are established, with their fungal and bacterial networks, the other trees and shrubs can start to move into the neighborhood. Gradually, sometimes over a century or more, these trees and shrubs go through their life cycle and a bit more organic matter builds up. Animal, rainfall, and bits of wind-blown sea wrack also bring more nutrients, and the forest becomes self-sustaining. I hope it's clear at this point how important the soil microbes are to a resilient forest. When we see the trees cleared and the topsoil stripped off in new developments, we're losing more than trees and soil. Commercial topsoil will be trucked in and the new lots will be landscaped, but without the extensive network of mycorrhiza and soil bacteria for support, the new plantings will be much more vulnerable to every type of stress, from drought to storm to disease. Those are the basics of how our forest got here, but what happens when things get rough? Disturbance is part of nature's cycle of renewal here, just as it is everywhere else. That's a little disconcerting, but we're best served by understanding what form it is likely to take and how the island ecosystem protects itself against catastrophic damage. Unlike many forested areas, fire plays a pretty limited role here. Major storms, with their associated wind load, flooding, salt intrusion, scour, and deposition are our major stressors. Barrier Island forests have adapted to survive these intense pressures. The structure of the individual trees and the way the trees interact with each other are the keys to their survival. Of the trees in our region, live oaks and palms have exceptional resistance to storm damage, though for very different reasons. So here we are, back at that beautiful live oak. Did you notice how the shape of the tree protects it? Many live oaks are broader at the base than they are tall, with huge branches extending to the ground. There's even more timber in the branches of the live oak than in the trunk. Think of the live oak as the sumo wrestlers of the tree world. Their center of mass is so low that it's very difficult to topple them. These low branches are part of the tree's protection, and limbing them up, or cutting off the lower branches, undermines their ability to withstand storms. You might also have noticed that the canopy is fairly open, letting the wind pass through the treetop with relatively little resistance. Finally, look at that trunk. There's a very good reason why for centuries shipwrights prized live oak timber for the keel of ships. Live oak wood is strong in nearly every direction in bending, tension, compression, and torsion. They're also wonderfully adapted to survive storms. Some of our other common oaks, the water and laurel oaks, have weaker wood and much shorter natural lifespans. They just don't have the live oak's ability to survive hurricanes. As you see here, pine trees do not fare as well either. In the aftermath of Hurricane Hugo, the National Forest Service surveyed the damage in coastal South Carolina. They found that while the live oaks were battered, they still stood. The pine stands were a near total loss. We've talked about the characteristics of individual tree species to resist storm destruction. But what about the forest as a whole? Here is a mixed stand of oaks. Can you see how the big branches will bang against each other and reinforce each other while they do it? The movement and impact in the canopy is dissipating the kinetic energy that might otherwise be directed against our roofs. We're all painfully aware of the damage that storm-down trees can do. As we think about how we want to live here, it's important to consider how an intact forest can protect us. Through a combination of salt pruning and natural canopy shape, forests guide the worst of the storm winds overhead. The limb-on-limb impact and the motion of the canopy absorbs and dissipates some of that storm energy. This is very different from what happens when storm winds pass over and between hard structures. Buildings don't absorb energy, they just bounce it off, so having lots of buildings around us doesn't help us much. If we are to make wise decisions about living with a maritime forest, we have to understand a little bit more about the mechanics of how they work. Let's take a look at trees from the perspective of materials engineering. First, we need to understand how composite materials work. They are all around us. If you have a carbon fiber golf club, tennis racket, or even surfboard, you already know about composites. So here's the formal definition. A composite material is a combination of at least two other materials separated by a distinct interface and, this is the important bit, has properties unlike its component materials. Here's a closer analogy to trees. This is steel-reinforced concrete. It's used in roads, bridges, and buildings. It works because steel and concrete have very different properties that, when combined, create a material with the best characteristics of both. Concrete is very strong in compression, but weak in tension, while steel is strong in tension, but prone to buckling under compressive loads. What does this have to do with trees? Everything. Think of tree roots as the steel. They're strong in tension, and soil, strong in compression, as the concrete. The combined root mass of all the trees and shrubs, the soils, and their soil microbes create a new material with different properties than any of them separately. Roughly speaking, a forested area has soil that is twice as strong as unreinforced soil, and areas with dense stand of prairie, marsh grass, or dune grasses are 2 to 4 times stronger than bare soil. This means that the plants are protecting our island from erosion. And, given that we all basically live on a sand spit, that is saying something. From the dune grasses to the east, to the forest, to the marsh grasses in the west, the native plants are so worthy of protection because they do such a good job of protecting us. When we think of how trees stabilize the island, the density of the forest stand matters. We don't have time here to go through the math, but the soil strengthening is proportional to the density of roots in the soil. This means that when we clear out understory trees and shrubs, or partially clear a forested stand, we've done two important things. First, the remaining trees are exposed to a new wind field, and second, the soil in which they are anchored is weaker. We know how to compensate for this, and we should. Sometimes we imagine that tree roots are evenly distributed, like in this idealized image. It's much more interesting than that. The roots orient themselves according to the prevailing stresses on the tree. So roots grow longer and stronger on the uphill side and toward the windward side. Heavens to Murgatroyd, someone cut that tree down quickly before it falls. Or not. These homeowners have the tree checked out by an arborist every few years and have taken a little weight off the top, but it has happily stood there for decades. Where do you suppose some of its most important roots are? If there was a need for a utility trench just to the left of the frame, the tree would be in real trouble. This reminds us that in construction, we should consider the specific circumstances of each stand of trees rather than relying on standard setback distances. Let's go a little deeper still and look at the different types of tree roots. Depending on the growing conditions, the roots may extend 2 or 3 times the diameter of the canopy. And regardless of their basic root architecture, tree roots adjust to the needs of the tree. There are 3 basic types: plate, heart, and tap roots, as you see here. Although in mature trees, the distinctions can get a little blurry. The next several photographs were taken as part of river restoration projects. No tree roots were harmed in the making of these images. As you might expect, plate roots run long and shallow. They're most common in species that grow in moist soils near riverbanks and wetlands. Plate roots have a bit of an unfair reputation as being weak, but as you can see here, they are capable of bearing nearly the entire weight of the tree and had done so for at least several months. Some pine trees and hickories have persistent taproots, and several trees, including the live oak, have a taproot when they're young. On the far right side of the frame, you see a taproot freshly exposed by advancing bank erosion. Finally, heart roots combine both features. Live oaks later in their lives tend to have this root architecture. Here is a disturbing image of a degraded urban stream. This sort of damage is unfortunately typical in communities without adequate stormwater regulation. When increased development adds more and more paving and other impervious surfaces to the land, rainfall reaches local creeks much more quickly, and this type of accelerated erosion follows. One small part of the restoration project for this area involved rebuilding a more natural shape to the stream bank and using a combination of hard engineering methods and native plantings. Happily, that big hackberry survived many more years. So, what's the best type of root architecture? A mix, of course. It's important to remember that even our largest trees rarely send roots more than a few feet deep. Roots don't go where there's no oxygen, water, or nutrients. The amazing thing about tree roots is their lateral spread, not their depth. Well-forested lands are more stable because tree roots increase the strength of the soil, making it more erosion resistant, and by the sheltering effect the canopy has on the understory trees and shrubs. Trees are impressive, but they're not invincible, as we know all too well. Here are a couple of images after Hurricane Matthew. As most parking lots do, this one has a turn-down wall at the edge to protect the paved surface from scour at the edges and for foundation stability. This severed the near-surface roots, and with a retention pond on the other side, the tree had no lateral stability on 2 sides. It would have been vulnerable to a minor storm that had dominant winds on its exposed sides. It certainly didn't help matters that the poor tree was planted in construction rubble. As the forensic arborist Dave Lippy says, trees don't fall down for no reason. If we reduce tree stability by limbing them up, unbalanced pruning or excessive root cutting, and by removing the understory, we have some responsibility ourselves for storm losses. One helpful way to think about our maritime forest is as our commonwealth and as part of our infrastructure. When we work with our forest, we gain some important benefits. Here are just a few. How can we protect the beauty, character, and benefits of our forest and still enjoy economic development? It's helpful to know that many communities have struggled with this question before us, and we have the benefit of decades of their experiences. The cornerstone of one successful approach is a discipline called conservation site design. Here, we seek to design in context. Rather than stripping the land bare, regrading it, and imposing all new infrastructure, we achieve our design goals, whether it's a subdivision, a commercial site, or institutional development, by studying how the undisturbed site works and mimicking that as closely as we can. This means working with the topography, the native vegetation, and the surface and groundwater flows as part of our design challenge. Of course, there is some site alteration, but by the end of construction, we have retained or replaced the natural functions of the site. We can also decide as a community that some land is most valuable just as it is. Understanding that no site is a blank slate is quite a challenge, but a rewarding one. Here's one example of an extremely difficult development problem that illustrates these concepts. The high plains of China east of Beijing don't seem like they have much in common with Amelia Island on the surface, but in some ways the two are not so different. We still have to deal with wind and water, soil and trees, while meeting the needs of a growing community. Here's the task. The city of Shenzhen added a new development of 50,000 people, with homes, schools, industry, a hospital, the works, all on 700 acres of former agricultural land. I was part of the team tasked with meeting the strict new water quality standards set by the central government. We were charged with treating all of the water on site to a degree that the lakes receiving that water were safe for fishing and swimming. We restored the forest fringe, created extensive wetlands that linked each aspect of the site, and managed the flow and depth carefully. By using the natural processes of trees, shrubs, and wetland plants, we removed the pollutants before the water flowed to the community lake. This is the Cliff Notes version of the process. The design team had close to a century of combined experience in just this type of project. It worked because we understood the function of each aspect of the landscape and made the deliberate design decision to integrate the built environment with the living world. We can make that same decision here regarding our own forest. If we do so, here are some actions to translate our intentions into reality. We don't have to invent anything new, but we do have to apply the best knowledge available to our own development challenges. Because, here on the edge, the health of our community is ultimately tied to the health of our maritime forest.